Okay. So tell you what, we're gonna ignore the blue screen of that. Light on will do. Hey, let's save half a gram of carbon. I think we're going to exhale more than that today. All right, so what are we talking about? What are we talking about Monday, Tuesday?
Let's look at Monday.
Okay. We had class Monday. It's a long time ago.
We have class on Wednesday.
Wednesday. Right. At least we knew we were going to the tournament that. Right? You had class Wednesday, but you didn't want to see me Wednesday. It was not pretty.
Bipolar Junction Transistors?
Bipolar Junction Transistors. Alright, so this is a picture of an NPN bipolar junction transistor. This is not really how they're fabricated. This is just kind of conceptual. They're fabricated kind of in layers, like we do with MOSFETs. Start with silicon, we dope, that's it for a BJT. But really, we'll stick with this model for a little bit because it's closer to our symbol in like shape, I guess. So NPN junction, bipolar. The bipolar actually is because there's electrons in holes participating in conduction in the current for both of these for this device. That's where the bipolar comes from. Also, you could think that the bi also goes with junction because there's two junctions here. You see two PN junctions, a PNN and a PNN plus. The N plus is just because we dope this side much heavier than the other side. And that's on purpose. It makes the transistor work better. It gives us a better gain, but it also makes it not symmetric. Remember, the MOSFET was symmetric. It didn't matter the drain or the source, especially on a chip. It did matter in lab because those were only 3-terminal parts, right? MOSFETs are really 4-terminal devices. Body connection on the bottom side. All right, so we have bipolar transistors. We get some current, some base current comes in here. Let's say it goes down this way. It makes a whole lot of electrons flow this way. Can you see how the electrons are emitted from the emitter side? And they're collected on the collector side? Yeah, that's why it's called the emitter and collector, by the way. And you know why this is called the base? Because that's what it's called, right? I mean, that's the test answer. It's called the base. Whatever. I don't know. So it's called the base. All right, so what happens is because this is heavily doped, we get a lot, we inject a few holes. Let's go H+, and we get a lot of electrons in the other direction. The asymmetry in doping makes that happen. It's because fusion. The diffusion part is injecting the holes in the base. We make a high concentration. The high concentration of holes travel this way because of the potentials here. And then we get electric fields between the collector and emitter, and they drift upwards. All right, so that's all nice. We're just not doing much of the physics, the semiconductor physics for these. We could, but then we would not have as much fun making them, putting them in circuits. All right.
So does it actually amplify the current?
Yes. These are current controlled devices. It's all about the current. You could call them current controlled transistors or current effect transistors, maybe. But it's not really current effect because it's like both diffusion and drift. And drift is electric field, so we can't just say current. Yeah. See what I mean? But field effect transistors, there is totally the electric field that determines what's going on. Alright, so symbol for an NPN. BJT, we have emitter, collector base. I'm going to do a Pnp transistor today also. These are the directions of the currents. Anytime we talk about collector current and it's an NPN, the collector current goes in. And that makes sense if you go back over to here. It's electrons going up, right? It's the electrons coming out of the collector terminal, which means the current's going down. Thank you, Alexander Graham Bell, right? That's just how it is. Holes are going into the base region. Holes are positively charged if we want to think of them as an entity, right? So they're going in. Electrons, both holes and electrons coming out of the emitter region, out of this terminal. So holes are going this way, current's going that way, electrons are going up. They're being emitted into the base collector region, but the current goes down because they're negatively charged. Okay. It turns out we can draw this. Let's go over here. Okay, you see a PN junction, right? Actually, you see two. Let's draw them. So here's the top PN junction. It goes PN going up, which means the diode arrow goes up. See that? The other PN junction goes this way. Spacing down. Okay, so here's our base terminal. Base current's coming into this node. Fair enough? Okay. Watch this. This is a PN junction. What's the parameter that we use when dealing with like voltages and currents with diodes, silicon diodes? Do you remember the equation? Vaguely, there's some terms in there that we need to know to come up with the current. Remember? The game doesn't start till like, what, 320? What is it? So we have a diode. We have V, AK, anode to cathode, right? But we have this equation, like ID equals something times EXP V diode over VT. What's the something? IS. All right, this is a diode, right? We're going to have an IS. Fair enough? It's not going to be exactly IS. We're going to call it IS over beta F. Beta F is a unitless number, so we still have units of current. This IS 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 over beta R. F and R for forward and reverse. So for this bottom diode, from the base to the emitter terminal, collector terminal, which way does normal diode current go? Does it go up? Does it go down? It goes in the direction of the arrow, so we're going to draw that. I'm going to call this what? We call this current IF over beta F. IF over beta F. These betas show up a lot. We're going to call this current going up. It's going up. It's going the direction of the diode. Currents can go up. That's okay. Right? What if your airplane flies upside down? Now there's no symbol, no ground symbol, and the currents are going up. Do you see how this could be a problem? I mean, this is like defense contractor sort of like craziness, right? Right? It's okay. PN junction. Let's draw the currents going the normal way so we don't get too confused. So this is IR over beta R. That current. Can we come up with IB now? Isn't it just KCL? Yeah, KCL. IB. Put this up here. IB. Here's what? IF over beta F plus IR beta R. I don't know if that's useful, but if we can do KCL, we might as well do it because it's just addition. All right. This is okay, but it's not a transistor yet. The magic action, not magic, is because this junction in the middle is shared between both of these junctions. It's the same material. If we just had two diodes back to back, we would do this, we'd be done. It'd be really boring. It wouldn't do much interesting. It'd be like two diodes connected with their anodes to the same node. So we're going to do this. We're going to do this. And we're going to make a dependent source. Make it go down. IT. You know what the T stands for? Actually, you can think of total, and that's fine. It really stands for transport. Because this is the unified the simplified, unified Gummel-Poon transport model. You know who came up with it first? Yeah, the two Japanese dudes. Okay? No chance with their first name. All right, so we actually have definitions for this. So IT forward current minus the reverse current. Total. Transport, total, close enough. All right, which way is the IF going? We draw this expression here, right? I say that the IT is going down. What arrow is associated with IF? Yeah, right there, right? You see that? Which way is IF going? It's going down. Fair enough. IR, it's reverse. It's kind of the big hint, right? It's going up. You add those together, they subtract. They like superposition of currents. Really? We have currents going this way, we have currents going up, we have currents going down. That's not a new concept. It's actually quite old, called mesh analysis. Do you remember that? So having currents going up and down at the same time is not a paradox or anything. It's just, I don't have a good joke there. Okay. Right, so it's just a superposition of them. There's only like electrons. You count the electrons, you watch where they're going. Good luck. And you just see the net. But we view it as two currents. The forward current going down, the reverse current going up. So the collector current, or collector terminal, emitter terminal. Collector currents and emitter current is still the same direction that we've defined for the symbol and everything. But do you see how IC is something? We can do KCL again. IC is IT minus IR over beta R. And if you look at your handout, you see that that's exactly what it says. Look at IC, the collector current. See KCL there. Okay. Except it's factored in a little bit. IS, here's our IS. This IS is the same for the transistor. The betas are different. EXP, V, lowercase v, Bravo Echo, base emitter. Lowercase upper means it's the total thing, right? This is like the physics. So whatever we do superposition, add all the voltages together, this is the total. And then BT, number, BT is Boltzmann's constant, temperature in Kelvin over charge of an electron. Or maybe 25, 26. Did you know it's inappropriate to say degrees Kelvin? Okay. Need to include a -1. Remember, we drop that -1 quite often, right? It's still there. It's really there. So IR, IS, EXP, little v, big base, big C, collector, BT, -1. All right, we all know what it means when we say VBC. You take the potential at the absolute potential at node B, subtract it from the absolute potential at node C, or take the difference between B and C, because we don't actually know the absolute potential. Right? It's always a difference. So VBC, VBE, they're different, even though they rhyme. All right, in your head, take IF minus IR. Take this expression minus this expression. You see what happens to the -1s? Do you see how they go away? Yeah, look at the first equation on the handout. You no longer have to wonder, I'm sure you were, before class started, where the -1s went. Right? They just went, they subtracted them off, and because they're in the same, right? All right, that's fine. I see. KCL. All right, so just KCL for the collector current. That's IT is going out. It's in the same direction. Minus IR over beta R. Even though the expression for IR over beta R, we have IR here. It's just divide this by beta R, and we get the second equation in the handout. Just kind of plugged in a little bit. The emitter current is IT. In what direction do we go? So IT plus this current, plus this diode current, IF over beta F. This dependent current source is here because that junction, that center junction, is shared and some interesting things happen. Is why. Otherwise, if it's just two diodes with true metal in the middle, like N type, P type metal, and then P type, then N type, then metal again, then we would have just two diodes and it'd be really boring. But because this is just a model, right? So we can split it out into things that we know. We have this, this is related to the current that actually skips the base region. It doesn't skip it, it goes through it, it sneaks past, floods past. There's so much that the base region can't do anything about it. Goes right through. So I think at this point it shouldn't be, if you've been not sleeping, too mysterious where these set of 4 equation comes from in the handout. It's really KCL and a couple definitions. IF, IR, KCL, we have these diodes here. These diodes have kind of a modified IS, just because we like to use the betas and such. All right, we're going to do the example next. I'm going to draw the picture that goes with the example. There we go. So VBB is attached to the base. Cheat sheet. Do we need a magic ground symbol? No, we don't have any node voltages. If we have a node voltage, then we need a reference, right? Because voltages, all the voltages that we work with are differences. So I'm not even going to put the magic ground symbol here because we don't need it. Okay, so we want IB, IC, IE. Right, so the blanks, start filling out the blanks. Fill in the equations symbolically. You can put in numbers later. The numbers are just what's in the example. You can do it, but fill out the equations. Maybe put in the numbers for VBC and VBE. Equations. What do you think about that? All right, do you have the table filled out? I'm going to take a picture quick. Okay, only about 8% of you have numbers down for BBE and BBC. I'm going for like 90%. Really easy. Numbers, one number. It's a Boltzmann, please. All right, so who has a number for BBE? Bravo Echo. Base emitter. If you don't, write it down. Write down like 42 volts and raise your hand. Still wait. Does this feel a little lame? I mean, like the mechanics of going through these equations, you just have to do it so your hands know what to do, and then you just do it automatically. So BBE, yeah, it's stretch time. Right? I've been working with my 11-month-old. He can do touchdown Nebraska now. So touchdown Nebraska, he's like, yeah. And then he's like, a little while later, he like looks over and he's like, touchdown Nebraska. It's either that or throw an interception. Last couple of years. Kind of sad. All right, VBE, what is it? It's 0.75, right? It's just attached to it. 0.75. Let's put a plus sign there. What's BBC? Be careful. Base to collector. Base node is at what potential?
0.7.
I have no idea. I kind of cut everybody off, right? What absolute potential is the base node at? I got no idea, right? Because I don't have a meter long enough to go infinitely far away from all charges. And even if I got it there, we've got a conductor like at the tip, right, which has free charges. Right, so let's go like this. This is when it's appropriate to add a magic ground symbol. Now we can talk about the potential at node B. So B minus 0 is 0.75 minus 0, so now we can say 0.75. Just got to drive it home. Right? We didn't really need it. We can do this minus this and whatever, KVL. All right, so this is 0.75 is the node voltage. This is 5. So what's B minus C? Go in this direction. Plus, minus. BBC is this one. Negative, right? Minus 4.25. Volts. Don't want to erase that. Can I erase the figure? Erase the figure. And let's work through the rest. So we have VBE, we have VBC, IT. Just plug it in. I'm just going to write down this. IS, we have a number for it, but I'm not going to plug it in. EXP. VBE, we have a number for that, which is 0.75 over 0.025 or 6.
6.
6? Warmer in here? Oops. Oops. Don't do that. It's not -1. EXP VBC minus 4.25 over 0.026. All right, here's a think question. How about this? We have VT here, right? We have VT here. Can these be at different temperatures? What does this equation mean? These are like the same junctions, the same physical material, right? I mean, one of those regions, the center region, the base region, is shared. It has to be the same temperature. See that? These two numbers have to be the same because that's physically what we're talking about. We're talking about the same bit of silicon. You can't have it at two temperatures at once. MATLAB will let you do that, no problem. The MATLAB says it's the language of science, or accelerating the progress of making mistakes or something, making it easier. I don't know. All right. So let's look at this. So we have, what's 0.75 over 0.026? Or maybe 750 over 226? 75 over 2.6? It's a big number, right? I don't care what it is. 28.5? 20, okay, so 29? Okay, good. All right, so e to the 29. Big enough, right? All right, remember this is like 10 to the minus like 15. So e to the 29. Can we drop this term? No, it's really big. All right, what's e to the minus 4.25 divided by 0.026? So just this inner term is like way bigger, right? Except it's e to the minus big number. What is e to the minus big number? I mean like really small, right? Like really, really, really small. So small, what we're going to do? 0. IC. IC is IT. Is up here. We have a number now if we want. We can get more accurate, but I mean we're talking like 7 digits out because it's going to change by keeping that second term in there. So IT minus IS over beta R. Beta R in this example is 1. Do you see the difference between beta F and beta R? 50 and 1? Even 50 is a little small. Although it's actually quite decent for a transistor on a chip. Whatever. The difference between beta F and beta R is because they're doped differently. The emitter's doped different than the collector, and that's why some of you had your transistors backwards, the emitter and the collector opposite, and it almost kind of worked until you flipped it around, and then it really worked. That's because the betas are quite different. So IS over beta R is just a number, we can't ignore it or anything. So EXP VBC 4.25 over 0.026 times 1. Look at this. Can we ignore the -1? Actually, let's not worry about the -1 yet, right? So we have EXP to the minus large number. Yeah, it's going away. Can we ignore the -1? 0 minus 1 is approximately equal to -1, right? We can't ignore the -1. All right, we have -1 times this, so we're going to say IT plus IS over beta R. Right, now IT is like EXP, IS, EXP, whatever, right? So really large number times IS. This is IS divided by 1 or so. So we have really large number times IS plus this, about this. Let's factor out the IS. Put back in the symbolic form, EXP VBE over VT, which is just this term, plus right, so even this term here, this IS term, we can almost drop that sometimes too, because this is a really small number. Base current. So the point I want to make with these, and like hacking through this, we're going to do the PNP right next, after I say my piece. So these equations, they're on your sheet, they're in the book. Takes up like half the page or a third of the page just to like barf them out, and that's why I put like typeset them in LaTeX, so I didn't have to write them out, and so you didn't have to like copy them down wrong, right? Because that happens. And I was going to copy them down wrong and then like erase it, and you're like halfway done writing in pen on a Friday. Do you see what happens? So we have some certain conditions. Look at this base emitter junction, BE. That is a PN junction, you see that? PN junction. I mean, the P is shared with both of them, right? But it's still a PN junction. Is this PN junction forward or reverse biased?
Forward.
It's forward. What about BBC?
Forward.
BC. So BC goes the way that the diode goes, right? But it's a negative number, which means this junction, this top junction, is what biased? It's reverse biased. Can you imagine that depending on how we apply the base, the collector, and the emitter potentials, how we apply those voltages, that we can have both forward biased, we can have the bottom one forward and the top one reversed, we can have the top one forward and the bottom one reversed, and we can have both of them reverse biased. Sure. You know what's great? These equations work for all of those modes. You don't even have to care. Plug and chug, man. I mean, there's a whole lot of plugging and chugging. But at least you don't have to think about it. right? But they work. It's really nice. There's none of this like a field effect transistor has what? Triode mode, it has saturation mode, it has velocity saturation mode, which we just don't talk about in 340 or too much, even though you have to deal with it all the time if you're going to make a real chip. Cutoff. We don't have those modes for a BJT. There's one set of equations that works for all modes. It's really nice. Do you want to use that one set of equations? They're kind of big. It's not that hard to memorize, really. Just throw in a bunch of exponentials, remember what the diodes are. Remember you have two betas, beta one direction, beta the other, whatever. You can memorize it if you want. But do you see what happens when we have one junction forward biased, the other one reverse biased? What's the current through a reverse biased junction, PN junction? Is it zero?
Very, very
Zero? No. It's not zero, but it's close enough. Especially when you got this one, right? When the other one's forward biased. So we can use a simplification that when that junction is reverse biased, that current contribution to KCL is just not there. Zero. That's where all the other equations for BJTs come from. And that's also why those other equations have conditions on them. We have to be in forward active mode. We have to be in reverse active mode. We have to be in cutoff or saturation. Those are just four different names for the four different ways of having those junctions, those two PN junctions. That's it. Just have names. And the reason we have two active modes is because the structure, that's not up here, the structure is almost symmetric. We call one forward active, the other one reverse active. And there's a distinction between them, unlike the FET. The MOSFET, there's no distinction between them. We don't have forward saturation and reverse saturation. The MOSFET, we have reverse saturation current and diode. It's a different name. Right, so it's just different names for all those four combinations. These equations work. The simplifications are because it just goes to zero. It's really small. Flip to the second page, and now we can do this one in 3 minutes. All right? So this is a symbol for a Pnp transistor. Which terminal is the emitter? Top one. It's emitting holes this time. Or actually, it's still. Right, so E, C, E. The currents are reversed. IC goes out, IE goes in. IB goes out. Follow the arrow. Writing in yellow on a whiteboard is a bad idea, but this is a yellow brick road, right? Follow it. Sing the song. You're good. Let's try it. You know the song, right? I was the Tin Man in middle school. My dad worked at a meat packing plant, so I was like truly the Tin Man because like on a meat packing plant there's like a lot of knives, you know what I mean? So there's like guarding on like for the employees, right? So I had like true aluminum shin shields and stuff. It was awesome. It's like dancing around, it's like all clacking. So forgot half my lines. I forgot half my solo too. Sang like the same verse twice, and I'm just like standing up there trying to, it's middle school. Just like, this is not going well. But it's not ending until we get this over with. It was a lot of fun. Those memories that kind of stick around for good or bad. All right, so PNP. Can you imagine how a PNP transistor looks? Not really a state secret. Right? Right? Which one is highly doped, the emitter or the collector? always the emitter. That's why we call it the emitter. So which one is the emitter? We go the same direction, the top one or the bottom P?
Top.
The top one. So it's P plus. Can you imagine we can draw the symbol mirrored vertically? Or whatever, right? Just look, if the arrow goes in, it's a PNP. If the arrow goes out, it's an NPN. Our next lab, we're using both. So, be ready. VEB. Why do we do VEB that way? I mean, it's like opposite, right? The p-type's always opposite of everything. Well, look at this. You see now why we do VEB? Yeah, because it's P to N. You still have a PN junction. Always think about the junctions in your go. And then, so what's the other way that we should do? This is what emitter, base, collector. What's the other potential that we need to deal with? It's the other PN junction. We're going to name it P to N, the normal diode way, which would be P to N, which is V C P. The base is still a part of both of those potentials. The equations are all the same. You still have the betas and whatever. The directions are different. That's page 2. I literally copy-pasted and did a search and replace on the capital letters. Swapped them around. That's it. Hit print. It's not cheating. It's just true. All right. Anyway, see you guys later. Have a great time. I don't think I'll see the game tonight, but let me know how it goes. It's exciting. Thanks for watching.